Hey, welcome back. So this is the second part of Lecture 5. Now we're going to talk about EARN models, in this part with replacement and ordered samples. And this is likely something you may have seen in high school even, but we're going to use sort of the constructions we've got from the previous lecture and the lecture before about sort of push forward via a random variable or distribution with respect to distribution of a random variable to link all these models together. Okay, so one example of an EARN model is where you could say have a population of people. All these people have individual names, but when you go and talk to a person, say you only request their age or say their voting preference or something, so you're not keeping track of all the information about the person. And then you could sort of take a list of these different people, but again, you only record some information about them, not the actual identity of the person. So the way that we're going to think about this is sort of via this EARN. So suppose we've got a big container and we've got some balls in it. And say these have colors. Okay, well, we could take n balls out of here and put them back after each time. So we take n balls. Okay, well, if we care about the actual numbering of the balls, then the reasonable sample space is going to be 1 up to 5 to the power of n. With its full sigma algebra, full power set as sigma algebra. But if we only actually care about the color, then the sample space that we should really be considering is red, green to the n. Okay, with its we're all in these discrete with finite sample space models, we're always going to be using the full power set as a sigma algebra. Okay, now as we mentioned in the previous lecture, we would like to think that given that we're putting the balls back each time, if we're using this sample space, then we should be equipping it with the uniform distribution, the uniform measure. And well, there's a clear random variable that goes from here to here, which just takes your sequence of numbers and spits out the corresponding colors of those balls. Okay, so we're going to use that to figure out the right distribution on here. Okay, so just to introduce some notation, we're going to have E is a set of colors, so finitely many colors. Okay, and then for A in E, there is some CA, which is a subset of, I should say 1 to n is a set of balls. Okay, and for each color, there's some subset of 1 to n, which is that color. So this would be the set of balls of color A. Okay, well then some conditions we need is that, the disjoint union of CA, that's an E, should be, the full set of balls. And if we let NA be the number of balls of each color, then, this implies that the sum of NA over the colors is equal to N. Okay, and now let's introduce our random variable, which is sort of, well, a silly one. So X from omega bar to omega is gonna, well, do exactly what we've said it should do. Color of omega 1 dot 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 color of omega n. Yep, and this is in omega. Okay, so let's figure out the push forward of the uniform distribution on here to here, and this is what we're going to call the EARN. Well, yeah, maybe we don't have a name for it, but it's the probability distribution on the EARN model. Now, given that we're working with finite sample spaces and their full power sets, as I've mentioned, I think in the first week of lectures, it's enough to figure out the probability of a singleton set here. So it's enough to figure out the density. And so let's do this. So push forward via X of the sequence of colors A1 dot 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 AN. Well, let's figure it out. So this is the uniform distribution on omega bar of X in this singleton. Okay, which is, well, omega bar has big N to the little n elements, and then the size of this set, we'll just write it out again. So it's omega 1 dot 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 omega n in CA1 cross dot 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 cross CAN. Okay, but the size of a product of sets is the product of their sizes. So this is 1 on n to the n times NA 1 times NAN. Okay, which is just the product over I equals 1 to n of NAI on n. Okay, this is maybe something you could have skipped right to, but we're just putting in a tiny bit of effort to use this push forward, because that's going to tell us some things automatically. Okay, and so it turns out that this probability distribution is actually a product measure, because, well, it's sort of, you want omega 1 to be in CA1 up to omega n in CAN, so there's some sort of product nature going on already. And, well, if we define rho of A to be just NA divided by n, well then this here, Px of A1 dot 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 AN is just the product of the row AI. Okay. Yeah, so a few small things to note here. Since we are replacing balls in this model, so we're putting them back in again, that's why we're using sort of the uniform distribution on this full collection of lists. This capital N plays no role, only the ratio does. and sort of you can think about that for a moment. It definitely makes sense. Another thing that we can note that is if E only has two colors, let's say 0 and 1, well then we could think of this as like fail and success, and the distribution that you get out of this process is then called the Bernoulli distribution. So if E is this, then this P of X is called the Bernoulli distribution. And this gives probability of a sequence of success or fail. Okay, so let's just figure out what the distribution in this particular case is. Well, let's say that row of 1, let's just call this P, and this we'll think of as probability of a single success. Well then, P of Px of A1 ... An is, well, it's P to the power of, the sum of the AI, okay, which is only picking up when AI is equal to 1, and then it's 1 minus P to the sum of 1 minus AI. Okay, and yeah, this is quite likely something you may have seen before, and if not, that's fine. Yeah, so you can also see this distribution, like we've said, it's only got two, it's a distribution on sequences of sort of binary checks on something. So you could also model it, use this to model flipping an unfair coin. So if P is not half here, then it's an unfair coin. If P is half, then it would be a fair coin. But then this sort of degenerates because P and 1 minus P are the same thing. Okay, we'll leave this lecture here, this part of the lecture. Yep.